it's a nice field. It's a nice field because it allows us to have, for example, tiny expanding universes in laboratories. So this is also a really well-known field. Myself, I also studied this during my master thesis, which I did in Heidelberg in the group of Stefan Floschinger. And we collaborated with a group of Markus Oberthaler. And what we had was a Bose-Einstein condensate. So this condensate was like a pancake. So it was tightly confined in this Z direction. And then there was like a trapping potential that generates this kind of disk condensate. And we use condensates because cold atom systems are highly tunable. And this allows us to introduce time dependencies and simulate this kind of expansion or contraction of the universe. So the question is how we introduce the time dependencies. So in this project, we introduce it just by being close to a Feshbach resonance and changing a magnetic field. And this changes the interaction between the atoms of the condensate. And also we change they change the trapping potential. And in that way, with this time-dependent perturbation, the particles created were phonons that behave as real massless relativistic scalar fields in a curved spacetime. So with this, I also want to show some experimental data in order to show that, of course, analog gravity is something that one can do experiments with. And yeah. So here I show some kind of the density of the condensate for hyperbolic space and a spherical space. And here one can see the when one turns on a blue deuterium laser in the condensate and then switch it off, and then we see how this wave packet, phononic wave packet, propagates through the condensate following geodesics depending on the curvature of the system. And another observable that one can check within this analog gravity of quasi-particle production is this two-point correlation function. So the gray curves are before the expansion or before the perturbation, and the blue curves are for after the time-dependent perturbation. And as you see, the two-point correlation function has now some peaks, some characteristic features of this two-point correlation function. And yeah, so this is an indicator of quasi-particle production. And here we can see how the density and the density contrast has changed before the ramp and after the ramp. So these large scale, these fluctuations in the large scale are an indicator of quasi-particle production. So with this, what I want to say is that, yeah, two-point correlation functions are a good detection tool for particle production, and we will use this also in this project of quasi-particle production in Dirac materials. So yeah, so as cold atom systems, moiré materials are also highly tunable. So initially we thought that maybe moiré materials were a good candidate to study this fermionic particle production. And yeah, since they are highly tunable, one can manipulate the band structure and the interaction between the electrons. And then, yeah, some of these materials belong to the Dirac materials, which are the materials in which we are interested to, because there the electrons effectively describe the Dirac equation. So they have some sort of linear dispersion relation, also known as Dirac cones. Yeah, so the most famous Dirac material is graphene. And let me introduce some basic properties of graphene. So graphene in real space is a honeycomb lattice. So it has two triangular sublattices, A and B, and this is the tight binding Hamiltonian that describes the electrons in the lattice. And then if we go to momentum space, we still have a honeycomb lattice. And if we focus on the first free ion zone, we see that in the edges of this hexagon, we find the Dirac cones, where we have this linear dispersion relation, and only two of these points are different. The others are related by symmetries. So we only have to worry about this K and K prime Dirac points. And in the Dirac cones, again, we have this linear dispersion relation, which describes massless relativistic particles. And yeah, here the slope of the Dirac cone is given by the Fermi velocity. But graphene is not highly tunable, so this Fermi velocity is pretty constant. But I said that moiré materials are the ones that are highly tunable. So if we add another layer of graphene on top of our monolayer, we have, and we twist it, we have twisted bilayer graphene that in the low energy regime, in the flat bonds, there are still Dirac cones protected by some symmetries, by time reversal and parity. And yeah, so these Dirac cones are also described by the Fermi velocity. And this Fermi velocity depends on the angle, the twist angle of the two layers of graphene. And it's interesting because for some angles, this Fermi velocity is roughly 0, and these angles are known as magic angles. So close to the magic angles, the Fermi velocity changes really, really fast. So this is interesting for our project in order to introduce time dependence. So what we suggest is that maybe one can introduce time dependence by a continuous rotation of the two layers, or by maybe applying some sort of pressure, which changes the magic angle, and then therefore the Fermi velocity also changes, or maybe applying non-interacting ultra-fast light pulses, because this also makes effectively the same effect, mechanical effect as pressure, and this makes the change faster, which is always interesting for us. So the idea of this project was to change the Fermi velocity in time from, for example, from this kind of Dirac cone, because it defines, or it describes, or gives the slope of the Dirac cone to another sort of Fermi velocity. So yeah, but this would be only an example to use twisted bilayer graphene for our project, but we want to keep it general. So let's take a Lagrangian for any kind of Dirac material. So here we have the Fermi velocity, which describes the velocity of our quasiparticles. And then here we allow also to have a gap, to open a gap in the Dirac cones. And this gap, we also allow it to be time dependent as the Fermi velocity, because when one introduces a time dependent perturbation in the system, you are not only changing that specifically that parameter, but maybe you can change others. So we want to make it general, so we introduce also a time dependence in the gap, and we allow also the gap to have a certain matricial matrix form, because this gap will be open in different ways depending on which symmetry we are breaking in the system. Yeah. So also in our project, we only studied gaps or masses that preserve Lorentz symmetry, because from the cosmological point of view, those are the ones that are interesting. And we want to make this connection with cosmological particle production. So that's why we choose this kind of masses. But of course, other kind of masses are interesting also, but not for this kind of analogy. And another thing is that for particle production, this mass term is essential, because this breaks conformal symmetry, and then this is what allows us to produce particles. So that's why we also introduce this gap. Okay. So now we want to find a relation with cosmology. So this slide is a little bit theoretical, so you can stop me at any point because there will be some formulas, and so here I took the Lagrangian for the general Dirac material that I showed in the previous slide, and I'm comparing this with the typical Lagrangian that one finds in curved quantum field theory textbooks. So this will be the spin connection coefficient, which is related to the curvature in the spacetime. Then these are the Filbine fields that are related to the metric of the system. This is a metric G, and then this is the cosmological mass. So just by comparing, one can obtain the Filbine fields and therefore the metric of this Dirac material. So the Filbine fields will be given by this matrix, and then the Filbine fields are connecting the Minkowski matrix with the metrics of the system, metric of the system in this way. And one can write the line element of the Dirac material. Okay. And now one can still compare another term. So one can compare the mass with this ratio of the gap in the Fermi velocity. So this will be the cosmological mass. And as I said before, this term is essential for particle production. But also what is essential is that this ratio between the gap and the Fermi velocity is time dependent. And this we will see in the next slides. But one thing is that in cosmology, normally the mass is constant. So one can perform Weyl scaling in order to obtain this mass to be constant and work in the constant mass frame. So one can perform this sort of Weyl scaling, which also transforms the mass in this way. And one can choose this function zeta in order to have a constant mass. So here we introduce this zeta in this way. So now we work in the constant mass frame, and also the metric of the system has changed. We transform the metric of the system in this way. Okay, so now the last ingredient that we need to introduce in order to compare it to an expanding FLRW metric is to introduce the conformal time. So the conformal time is introduced as the Fermi velocity times the real time. And now we get this line element, and now we are prepared to compare it to this FLRW metric of an expanding universe. So in this metric, we see this scale factor. This scale factor is the one that governs the expansion or contraction of the universe. And we can compare this metric with the metric of the Dirac material, and we see that this term and this term are the same. So we have here a time-dependent prefactor that we can say that it's equivalent to this scale factor that governs this expansion or contraction of the universe. So this is nice because this means that changing the ratio between the Fermi velocity and the gap. So for example, increasing this ratio, this means that one can simulate an expanding universe, and decreasing the ratio between the Fermi velocity and the gap, one can simulate a contracting universe. So now we have this connection with cosmology, and what we want to do is to solve this Dirac equation for different gaps and for different time dependencies in order to simulate different kind of expanding universes. So in order to do that, first one has to choose a convenient basis for this Dirac field. So now we have this Dirac equation, and a convenient basis for the field will be this one, for example, because if you remember in the first slides where I showed you graphene, I showed you that graphene is formed by two different sublattices, A and B, and we have two different Dirac points, K and K prime. So for our system, this will be a convenient choice. And now one can expand this Dirac field in Fourier modes, for example. So in our project, we work in flat space, but one could work in a spherical or hyperbolic space just by changing this this function here, substituting this by the corresponding function for each geometry. So in this expansion of the field, what we see is that this contains all the space dependent of the field. And then now we have here C and D. C and D are the fermionic and antifermionic operators, and they describe the vacuum of the system. And now we have here two more terms, two more ingredients that are U and B. And if you remember, eta is the conformal time. So U and B are the mode functions, and these functions contain all the time dependence of this wave function. So when we plug in this expansion of the field into the Dirac equation, only the mode functions will be relevant in order to study this time dependence of the system. So, okay, let's see. So as I said, the time dependence is fully contained in the mode functions. And if we plug in the expansion of our field into the Dirac equation, we have this coupled system of first order time derivatives of the mode functions. And this ratio is where this time dependence of the system is contained. So in order to study this, these equations, in order to study particle production, what we suggest is that we divide our time, our conformal time, in three regions. So we have a first region that is stationary, then we apply a time dependence, a time-dependent perturbation. So here we are seeing always the ratio between the gap and the Fermi velocity. And then we have another stationary region. And so we need these two stationary regions because in these stationary regions, one can define vacuum, and is where the concept of quasi-particle makes sense. One cannot define quasi-particles when we have a time-dependent perturbation, when things are changing in our system. So in the first region, we have C and D as operators, and then we have this vacuum omega. And in the third region, since it's after the time-dependent perturbation, one has to introduce new operators, C tilde and D tilde. And then we have a new vacuum state also that are omega tilde. Okay, and then in order to study better this system, one can couple these two differential equations, and we get this kind of second order differential equation where we have again this time dependent ratio here, and also in this frequency. And this sort of second order differential equation, I don't know if reminds you something, but it looks like an oscillator differential equation with a frequency that is time dependent and complex. So if we focus on the stationary region, so in region 1 and in region 3, we see that this term vanishes because it's a time derivative of something that is constant now. Because if we are in the stationary regions, this is constant, and this term will be just a frequency. It's a constant frequency. So the solution for this equation, differential equation in the stationary regions, is just the Minkowski mode in this way. And now the question is how these two regions are related. And the answer is they are related through Bogoliubov transformations. And I did all this because the Bogoliubov coefficients are related to the observables of quasi-particle production. So now one has to ask how the Hamiltonian of the system has changed, because initially we have a Hamiltonian that is diagonal in the operators C and D. Now we have a time-dependent perturbation, and now the question is how the Hamiltonian looks like, because it's not going to be diagonal in C and D anymore, but one can do a Bogoliubov transformation and diagonalize the Hamiltonian and find the new basis that will be C tilde and D tilde. Okay, so after the time-dependent perturbation, the Hamiltonian is not diagonal, and we have these new functions, E and F, that depend on the mode functions U, so from solving the Dirac equation. And one can diagonalize it through a Bogoliubov transformation, and now the Hamiltonian is diagonal again in this new basis. And yeah, one can obtain the Bogoliubov coefficients, and which are related to the mode functions. And yeah, the Bogoliubov coefficients satisfy this relation because we are working with fermions, so they satisfy the Pauli exclusion principle. All right, so this will be all the theory, all the ingredients that we need in order to obtain some results. So in order to study quasi-particle production, the first observable that we check is the quasi-particle occupation number. So we take the number operator in the new basis, so C tilde, daga C tilde, and we apply it in the initial vacuum state. And this corresponds to the absolute value square of the Bogoliubov coefficient beta. And if this is different from 0, then this is an indicator of particle production. And here we see a plot. So in this case, we have changed the Fermi velocity in this range, and also the gap in this range, because we chose some numbers that will be feasible in the case of twisted bilayer graphene. And then we see here a signal, so this is an indicator of particle production. But now the question is, what happens if we don't start from an initial vacuum state, but we start from a state that there are already some sort of excitations? So for example, we pick initial thermal state. So we start with this kind of particle density distribution, the Fermi-Dirac distribution. So we see that the higher the temperature, the lower is the signal, less particles we produce, because this is due to the effect of Pauli blocking. Yeah. And this is because if we have already fermions in an initial state, we cannot create more fermions where there already are fermions. And the opposite will happen in the case of bosons, because bosons are social particles, and then having initial state with bosons, this will increment the particle production. It will make the opposite effect. Okay, so this will be the first observable, and the second observable, as I said in the beginning, with the case of Bose-Einstein condensates, is 2-point correlation functions. And in this case, 2-point correlation functions are interesting, many of them, but here I only chose this one, which is related to the staggered density contributions on the sublattices, so the difference in the densities in the two different sublattices that we have. So here we see again the effect of having an initial thermal state. So the higher the temperature, again, the lower is the signal. So the lower are these characteristic features of this 2-point correlation function. And something that is interesting from these 2-point correlation functions is that even if we are in a static regime, because this we measure in region 3, so where Fermi velocity and gap are constant in time, we see that the characteristic features of these 2-point correlation functions evolve in time. So this is the holding time. So how much time has passed since the perturbation has ceased. And we see that these peaks are propagating in time. And this is because we are studying two-point correlation function. So we are studying 2 points, and these excitations are not static. They are still moving with final Fermi velocity. So we create this kind of cones. Okay, so this will be from the theoretical point of view, but of course, analog gravity aims for an experimental realization. So the question will be, what is essential for this experimental realization? And the answer is, as I said before, that we need a bandgap because this breaks conformal symmetry. And what we need also is this time-dependent ratio, because if there is no time-dependent ratio, then yeah, it's yeah, you don't apply. It's like not applying any kind of perturbation. So the possible or the suggestions that we have for this experimental realization would be twisted bilayer graphene in the vicinity of magic angles. So maybe applying some hydrostatic pressure that changes the magic angle and the properties of twisted bilayer graphene, or maybe applying ultrafast light pulses that have the same mechanical effect as pressure, but this allows us to make the time-dependent perturbation faster, so the change can be made faster, or maybe performing a continuous rotation of the two layers. But yeah, this has been done already in Israel at room temperature, but they have not managed yet at lower temperatures, which is the regime in which we are interested in. And then another kind of experimental realization that we suggest would be with Bernal stack bilayer graphene, where here you can see that one can open a gap through an electric field, applying a displacement field. And now the slope of the Dirac cones is constant. So this means that the Fermi velocity is fixed, but we have a time-dependent gap. So this ratio is already time-dependent if one of them is time-dependent. Of course, it's not necessary that both Fermi velocity and gap are time-dependent. And our last suggestion would be honeycomb lattice, generate some kind of optical lattices, like a honeycomb lattice, to trap cold atoms, because as I said initially, cold atoms are highly tunable. And then the idea will be to make different potential depths in the two different sublattices. And this generates to open a gap in the Dirac cones. So again, the Fermi velocity will be constant, but we have a time-dependent gap. Yeah. So this will be my conclusions. So as we saw, Dirac materials can be good quantum simulators for quantum field theories in expanding spacetimes. Then we saw that what is essential is to have a gap in these Dirac cones in order to have particle production, and to have a time-dependent ratio between the gap and the Fermi velocity, but that is not necessary that both of them are time-dependent. With one, it's already enough, and that this time-dependence does not cancel between them. And then we saw also that correlation functions give signatures of particle production. So yeah, this will be also the outlook. There are a lot of things to explore. For example, one could consider to introduce gauge fields, which will allow us to study, for example, the Schwinger effect, or maybe to introduce spatial curvature, so not expanding the field in Fourier modes, but yeah, in a different way. And maybe also it will be interesting to use analog gravity in order to reproduce or understand better unsolved cosmological problems like baryon-antivarion asymmetry. And of course, we would like to have some sort of experimental realization of our project. And with that, I would like to thank again my supervisors, Stefan Floschinger and Michael Scherer. And yeah, also you for your attention. Thank you.
Okay, thank you very much, Mireia. Really nice talk. Thanks very much again. Do we have any questions immediately from the group? Feel free to raise your hand or just unmute yourself and ask. You can also use the chat if you prefer. So I suppose I'll ask the kind of obvious question just to kick things off. Is there any sort of pathway at the moment towards an experimental realization for this, or is it still at the kind of brainstorming phase at the moment?
So we are in contact with some experimental group that have a Bernal bilayer stack graphene, but yeah, we are still working on it. We still don't know what is best platform. We think that maybe honeycomb optical lattice to trap cold atoms is the best one, but we have not talked with any group yet. Yeah.
Ian.
Hi, let me just start my there we go. Hi, that was very interesting. Thank you very much. I've not seen this kind of stuff before, but I've seen work on looking at spatial variations of graphene. For example, graphene on a substrate that's not planar. Does this link into that as well? Can you vary the Fermi velocity as a function of position as well as a function of time?
Yeah, so varying the Fermi velocity as a function of position of space, this will lead to have some sort of spatial curvature. So if the velocity is in additional space dependent, then probably this spin connection is, so 1 second, I find the formula. Yeah, this spin connection would be also space dependent, and then the solution for the Dirac equation will not lead to Fourier modes anymore, as we have here. We will have something different.
And can the Fermi velocity be driven through zero? For example, can you have an analog black hole just in the graphene properties?
A black hole in so using graphene or?
Yeah, look, it's a wild question.
So I'm not sure if with graphene would be possible. I know that there are studies or papers that mention Bose-Einstein condensates with vortices in order to reproduce curved black holes or rotational black holes. But I think with graphene, I don't think this would be possible because we cannot reproduce this kind of black hole properties, I would say.
So you can't drive the Fermi velocity to zero at some point at some region in space, can you?
Yes, theoretically, but experimentally, I'm not quite sure about this. You can vary the Fermi velocity in a range of 10 to the 3 orders of magnitude of 10 to the 4, but reaching zero experimentally, I think it's not that easy.
Okay, it's a crazy question. Anyway, thanks for the answer.
Yeah, thanks, Ian. Duncan.
Yeah, thanks, Mireia, for the nice talk. You mentioned at some point that this could be your equations of motion could be thought of in terms of an oscillator with a complex frequency. Is that right?
Mm-hmm. Yeah. So this will be the differential equation that we have to solve, and this is imaginary part. That if you consider this as the frequency of this oscillator differential equation, this will be a frequency that is time dependent because it has this ratio, and also that is complex, to say so.
So it's not that you're mapping onto an inverted harmonic oscillator or anything like that. You have a dynamical instability where your frequency is becoming complex.
Yeah, I think this just comes from the choice of gamma matrices, and yeah,
One could move it around to other related problems, possibly. Yeah. Like I'm just thinking of Landau-Zener or something like this, like mapping it onto that.
Okay.
Like treating this as a non-adiabatic effect.
So non-adiabatic is no, because if not, we will not have particle production. So it's a non-adiabatic process. But I have not thought about what you said before.
But you think that the Bogdanov transformation, it's all well defined, even if the frequencies are complex. It's
no, but I mean this one can solve. I mean, I put this differential equation in Mathematica, and I have a solution for you and for the mode functions. And then the only thing is to relate to ask how these two regions are related, and the answer is that they are related through Bogoliubov transformations. Yeah. And
okay, so it's you don't worry about non-Hermitian effects like the mode functions might not be orthogonal anymore and these kind of effects, or
so from the definition of my fields, they are orthogonal, but I don't know, like I have not considered if there is some
so
sort of
it seems to go through no problem
yeah
with the complex frequencies. I see. Okay, thank you.
Okay, thank you, Duncan. Michelle, you had your hand up for a moment there. Is there anything you'd like to add?
Yeah, I mean, I can just very briefly add something to Ian's question concerning whether the Fermi velocity can be driven to zero. So in these moiré systems, the twisted bilayer graphene, there is the Fermi velocity is a function of the twist angle, and for certain twist angles which we call the magic angle in condensed matter physics, at least theoretically, the Fermi velocity is zero. The challenge there is that you then get, well, when you have such a small Fermi velocity, your kinetic energies of the electrons, they are suppressed. That means that you cannot ignore the potential or the Coulomb energies anymore. And then you are getting into a strongly correlated state. And this makes the problem very complicated again. So you're getting a new problem for that. That's everything I wanted to say.
Okay, thanks. Are there any final questions which anyone would like to ask for Mireia? Okay, if not, then thank you again, Mireia, for a great talk. And that will be the end of today's session. So I believe this is the final session that we have scheduled currently. If there are any new up-and-coming talks planned, then I'm sure Vanessa will reach out and let everybody know. But for the time being, thank you all for joining.
Thank you.